Welcome to G Fun Facts Online. Today, we are going to completely rethink how we search for aliens. For decades, the hunt for extraterrestrial life has been a hunt for noise. We have been listening for the technological hum of radio waves, or looking for the loud spectral scream of oxygen and the sharp chemical spike of methane. We have spent 50 years looking for what life adds to a planet. We look for the waste products, the artificial signals, the chemical imbalances. But a paradigm-shifting study published in late 2023 by an international team of astronomers has flipped this logic entirely on its head. The most potent sign of life on a temperate, rocky exoplanet may not be what is there, but what is missing. This concept is called the Carbon-Lite Atmosphere. It proposes that if we find a terrestrial planet that is significantly depleted of carbon dioxide relative to its neighbors, we have found a smoking gun for liquid water oceans and potentially a biosphere. This is a story about how less is actually more, and how the silence of a missing molecule might scream louder than any radio signal ever could. To understand why this new hypothesis, led by Amaury Triaud of the University of Birmingham and Julien of MIT, is so revolutionary, we first have to understand the wall that exoplanet science has hit. We are currently in a bit of a bind. Since the discovery of the first exoplanet orbiting a sun-like star in 1995, we have confirmed over 5,500 worlds. We have moved from the era of simple detection, knowing they exist, to the era of characterization, figuring out what they are made of. For a long time, the holy grail of this field has been molecular oxygen. On Earth, oxygen is a volatile reactive gas. It loves to react with things. If you turned off all the plants and algae on Earth today, our atmospheric oxygen would vanish in a few million years, reacting with the rocks in the crust. Therefore, finding a planet with a lot of oxygen, especially alongside a reducing gas like methane, implies that something is constantly replenishing it. That something is usually life. It is what we call thermodynamic disequilibrium. But here's the problem. Detecting oxygen on a rocky Earth-sized world orbiting another star is excruciatingly difficult. The spectral signals for oxygen, specifically the A-band at 0.76 microns, are weak. They're easily drowned out by instrument noise or blocked by clouds. Furthermore, accumulating enough oxygen to be detectable took Earth's biosphere billions of years. If we only look for oxygen, we are limiting ourselves to finding planets that are not just alive, but advanced in their evolutionary timeline. The James Webb Space Telescope, or JWST, is a technological marvel, but even for Webb, confirming an oxygen atmosphere on a prime candidate like TRAPPIST-1e could take hundreds of hours of observation time. We are talking about years of the telescope's life dedicated to a single target, with no guarantee of success. We needed a signal that was stronger, clearer, and indicative of the conditions for life, rather than just the metabolic waste products of life. This is where the Carbon-Lite Atmosphere comes in. The insight for this theory didn't come from staring at deep space. It came from looking at our own backyard, the solar system. If an alien astronomer were observing our solar system from 40 light-years away, they would see 3 rocky planets in the temperate region of our Sun: Venus, Earth, and Mars. To a low-resolution telescope, these 3 worlds would look like siblings. They are peas in a pod. They were formed from the same protoplanetary disk, roughly at the same time, from roughly the same materials. You would expect them to be chemically similar. But if that alien pointed a spectrometer at them, they would see a massive anomaly. The atmosphere of Venus is roughly 96.5% carbon dioxide. The atmosphere of Mars is roughly 95.3% carbon dioxide. And Earth's atmosphere is 0.04% carbon dioxide. Venus and Mars are dominated by carbon. Earth is carbon depleted. The question is why? It is not that Earth has less carbon in total. In fact, Earth has a massive inventory of carbon comparable to Venus. The difference is where that carbon resides. On Venus, the carbon is in the sky, creating a crushing 92 bars atmosphere that turns the surface into an oven. On Earth, the carbon is not in the sky, it is underground. The mechanism responsible for Earth's missing atmospheric carbon is the silicate weathering thermostat. This is a geochemical cycle that absolutely requires liquid water to function. Let's break down how this works, because it is the engine of the Carbon-Lite hypothesis. It starts with rain. In an atmosphere containing CO2, rainwater absorbs the gas to form weak carbonic acid. When this acidic rain falls on silicate rocks, the continental crust, a chemical reaction occurs. The acid dissolves the rock. This weathering process captures the carbon molecule and creates calcium ions and bicarbonate ions, which are dissolved in the water. These ions wash into rivers and eventually flow into the ocean. Once in the ocean, marine organisms like corals and microscopic plankton use these ions to build their shells and skeletons out of calcium carbonate. Even without life, abiotic precipitation can do this, but life helps. When these organisms die, or the chemicals precipitate out, that calcium carbonate settles on the ocean floor as limestone. The net result is that for every molecule of silicate rock weathered by rain, one molecule of atmospheric CO2 is locked away in solid rock on the ocean floor. This carbon stays locked away for geological timescales, unless volcanoes recycle it. But as long as you have liquid water oceans facilitating this rain and runoff, the standing inventory of carbon in the atmosphere remains low. Therefore, a rocky planet with a carbon-light atmosphere, relative to its neighbors, is a planet that possesses liquid water. It implies an active hydrological cycle. The brilliance of Triaud and DeWitt's proposal is that it solves the problem of cosmic variance. If you look at a single isolated planet and see low CO2, you don't know if it is depleted or if it was just born empty. Maybe that part of the galaxy just didn't have much carbon. This is why the strategy focuses on multi-planet systems, specifically those dubbed peas in a pod, systems where multiple rocky planets orbit the same star in a compact configuration. The TRAPPIST-1 system is the perfect archetype for this. TRAPPIST-1 hosts 7 rocky planets. Planets B, C, and D are too close to the star. They are likely runaway greenhouse worlds, similar to Venus. Planets E, F, and G are further out, sitting in the habitable zone. The strategy is comparative planetology. First, we survey the hot planets, B and C. We measure their atmospheres. If they are carbon-rich, like Venus, we establish a baseline carbon inventory for the system. We know that the star system formed with plenty of carbon. Second, we survey the temperate planets, like TRAPPIST-1e. We measure its atmosphere. Finally, we compare. If planet E has significantly less CO2 than planet B, that carbon must have gone somewhere. Since planets in the same system form from the same material, the carbon should NT just be missing from the start. The most likely sink for that missing carbon is the planetary crust, sequestered by liquid water. We don't need to know the absolute abundance of carbon in the universe. We just need to know the relative abundance between siblings. But this theory goes deeper. It's not just a sign of water. It could be a sign of life itself. We call this a habiosignature, a mix of habitability and biosignature. Life accelerates carbon depletion. On Earth, roughly 20% of the total carbon drawdown is attributed to the biological pump, marine biomass, sinking to the ocean floor. Furthermore, biomass itself is a reservoir of carbon. A massive planetary biosphere captures carbon from the atmosphere and stores it in forests, soil, and peat. If a planet is extremely depleted in carbon, even more so than simple inorganic weathering would predict, it suggests an active biosphere is aggressively scrubbing CO2 from the air. To confirm this, the researchers propose a secondary check: ozone. Ozone is a proxy for oxygen, but it is much easier to detect because it has a strong absorption feature in the UV and infrared. If you see a carbon-light atmosphere, which confirms water, and you also see ozone, which confirms an oxygen source, the probability of life skyrockets. The combination of water and oxygen is chemically inconsistent without a biological driver. Now, why is this method better for the James Webb Space Telescope? The practical advantage is detectability. Carbon dioxide is the loudest molecule in the infrared spectrum. The JWST, specifically its NIR spec prism instrument, is sensitive to a wavelength range that includes a massive, booming absorption feature of CO2 at 4.3 microns. This feature is so strong that even a thin atmosphere with a small amount of CO2 will show a distinct dip in the spectrum. Contrast this with water vapor or oxygen. Their spectral features are fluffy and broad. They can easily be hidden by clouds or hazes. The 4.3 micron CO2 band is less affected by hazes because it sits at a longer wavelength. Physics tells us that hazes scatter short wavelengths more, a phenomenon known as Rayleigh scattering, so the infrared light punches through better. Let's look at the math of observation. To just confirm an atmosphere exists on TRAPPIST-1e via CO2 might take about 10 transits. To measure the abundance precisely enough to claim depletion might take about 40 transits. To detect ozone, the hardest part, might require 100 transits. While 40 to 100 transits is a large investment, it is feasible within JWST's lifetime. Attempting to detect the oxygen A-band directly on an Earth-like world with current technology would likely be impossible. So let's simulate how a carbon-light discovery would play out over the next few years. In the first year or two, astronomers point JWST at TRAPPIST-1b and 1c. These hot worlds are roasted by their star. The spectra come back showing deep absorption at 4.3 microns. Models indicate atmospheres composed of over 90% CO2 with crushing surface pressures. We have confirmed the system is volatile rich. The siblings have plenty of carbon. In years 3 and 4, the telescope turns to TRAPPIST-1e. This planet sits squarely in the habitable zone. We effectively have 3 scenarios. Scenario A is the dead rock. The spectrum returns a flat line. The planet has no atmosphere, likely stripped away by stellar wind. The result is a non-habitable world. Scenario B is the Venus twin. The spectrum shows a massive 4.3 micron dip, identical to planets B and C. The atmosphere is 95% CO2. The result is a runaway greenhouse, likely too hot for life. But then, there is Scenario C, the Carbon-Lite world. The spectrum shows a CO2 feature, but it is weak. Detailed modeling suggests the atmosphere is dominated by a transparent gas, like nitrogen, which is spectrally invisible, with only a fraction of a percent of CO2. If Scenario C occurs, we have to ask, where did the CO2 go? Did it escape to space? Unlikely, because nitrogen is lighter than CO2. If the atmosphere was being stripped, the lighter nitrogen should have been stripped first. Is it in the crust? The only known mechanism to bury that much carbon into the crust of a rocky planet is the carbonate-silicate cycle. The conclusion is that TRAPPIST-1e has liquid water oceans dissolving its atmospheric carbon. Of course, no biosignature is perfect. We must play devil's advocate and look for false positives. One possibility is the stripped core. Could a planet lose its atmosphere physically, rather than chemically? If a giant impact blew away the primordial atmosphere, the planet might reform a thin secondary atmosphere that looks carbon-depleted, but is just empty. However, this is why the nitrogen detection is key. If we see a bulking gas like nitrogen, inferred by the pressure broadening of spectral lines, but low CO2, physical stripping is less likely because it wouldn't selectively remove just the heavy CO2 while leaving the light nitrogen. Another false positive is the ice world. A planet further out might condense CO2 into dry ice caps, like Mars but more extreme. If the CO2 is frozen on the surface, it is in the atmosphere. But for a habitable zone planet, it should be too warm for massive global CO2 collapse, unless the planet is already in a snowball state, which is technically still water, just frozen. There is also a potential false negative, the young Earth. In the Archean eon, roughly 3 billion years ago, Earth had life, but it also had much higher CO2 levels than today, perhaps 10 to 100 times higher. This was because the sun was fainter, and a stronger greenhouse effect was needed to keep water liquid. If we saw Archean Earth from space, we might not see it as carbon-light enough compared to a Venus analog to trigger the detection. This implies that the Carbon-Lite signature is best at detecting mature biospheres or planets with established geochemical cycles. It might miss the baby Earths. Looking beyond JWST, the Carbon-Lite concept is a foundational tool for the next generation of telescopes, like NASA's future Habitable Worlds Observatory. This mission aims to take direct photos of Earth-like planets. When we look at a planet directly, we analyze the light reflected off its surface. A Venus-like world appears bright and featureless due to thick clouds. A Carbon-Lite world, like Earth, has a thinner, clearer atmosphere. We might see Rayleigh scattering, the blue sky, and potentially surface features. The Carbon-Lite metric helps us prioritize targets. If the observatory finds a system with a bright carbon-rich inner planet and a dimmer carbon-poor outer planet, the outer one becomes the primary target for deep integration to look for the green of chlorophyll. In conclusion, for too long we have equated the search for life with the search for noise. We look for the loud chemicals and the radio waves. But the Carbon-Lite atmosphere hypothesis reminds us that life is also a consumer. It eats entropy. It processes raw materials. It alters its environment by sequestering resources. A habitable planet is a balanced planet. It is a world where the violent volcanic outgassing of carbon is tamed by the soothing cycle of rain and rivers. When we look at the spectra of distant worlds, finding a massive gap where carbon dioxide should be might be our first indication that we are looking at an ocean, a water cycle, and perhaps a home. In the hunt for life, the most profound signal might just be the silence of the carbon that isn't there. Thanks for listening to G Fun Facts Online.